Hi, this is Tyson Auctioner, and I want today to help you understand soil-water potentials in systems at equilibrium. On the left side here is a soil column, and the dashed line here represents the soil surface. The soil column at the surface, we're going to call that point A, and down below we'll call point B. In this case, the soil column is 30 centimeters long. We had a reservoir of water here on the right, and this triangle shows that the surface here is at atmospheric pressure. We want to now connect this reservoir hydraulically to the soil column, and so this line represents a hydraulic connection between the water reservoir and the bottom of the soil column. Whenever we are ready to analyze soil water potentials, it's really helpful to draw a table like the one shown here. So you label for each of the points you want to consider columns. So here we have columns A and B, and we have rows corresponding to psi subscript G, that's the gravitational potential, psi P is the pressure potential, psi T is the total potential. Now in this case we're neglecting osmotic potentials, and we're just treating the total potential as the sum of the gravitational and the pressure potentials. Notice also that we're keeping track of our units. For each row, the units are going to be in centimeters of water. We're almost ready to begin filling out our table, but before we can do that, there's one really important step we have to take care of: to specify a reference elevation. And that's shown here. Here I've chosen to put the reference elevation at point B. This choice is arbitrary and is just made at the bottom here for the sake of convenience. If B is my reference elevation, then by definition, the gravitational potential at B is going to be 0. Point A is 30 centimeters above my reference elevation. Therefore, the gravitational potential at A will be 30 centimeters. So we can fill that in our table. Next, we're going to look at the pressure potential at A. Notice that A is on the same elevation with and hydraulically connected to the free water surface. Therefore, the pressure potential at A, when this system is at equilibrium, must be equal to atmospheric pressure, or 0. The total potential at A then is simply the sum of the gravitational and pressure potentials, so that will be 30 centimeters. The total potential at B has to be equal to that at A when the system is at equilibrium. That's what equilibrium means. The total potentials are the same throughout the system, so it has to be 30 in both cases. Well, now we have only one blank left in our table, and we can see just by quick inspection the pressure potential at point B must be 30 centimeters. That makes sense because it's 30 centimeters below this free water surface and hydraulically connected. So there's our first example. What if we change things up a little bit? Now we've moved the free water surface. In this case, the free water surface is only 15 centimeters above the bottom of the soil column. Our reference elevation is still in the same place. Let's see what our table would look like now. Our gravitational potential at B is still 0, and our gravitational potential at A is still 30 centimeters. However, our pressure potential at B is changed. Now point B is only 15 centimeters below the free water surface, so its pressure potential is positive 15 centimeters of water. The total potential at B then is going to be 15 centimeters of water, and since it's at equilibrium, we know the total potential at A. It is also 15 centimeters of water. Again, by quick inspection, we can see what the pressure potential at A must be. It must be 15 centimeters minus 15 centimeters of water in this case. So we have 30 centimeters for the gravitational potential minus 15 centimeters for the pressure potential, giving us a sum of total potential of 15 centimeters. And we can continue this and change the example once again by further lowering the water reservoir. Now we have the free water surface equal in elevation with the bottom of the soil column. Gravitational potential is always where we start, and the gravitational potential at B is 0. At A is 30 centimeters. The pressure potential at B, we know, has to be 0 because it's at the same elevation as and hydraulically connected to the free water surface. Therefore, the total potential at B is 0. Since the system's at equilibrium, then the total potential at A is 0. Therefore, the pressure potential at A has to be minus 30 centimeters. Now, I want to make sure you caught one important point regarding the reference elevation. Remember, the choice of the reference elevation is arbitrary. What if we change the reference elevation to be here, at the top of the soil column, rather than the bottom? In this case, we would find the gravitational potential at A is 0, and the gravitational potential at B is minus 30 centimeters, because it's 30 centimeters below our reference elevation. The total potential at B then would become minus 30 because the pressure potential hasn't changed. The free water surface is still at elevation B. So that pressure potential is still 0 and the total at B is now minus 30. Total potential at A likewise must be minus 30 because the system's at equilibrium and their pressure potential at A is minus 30. I hope these simple examples have helped you understand how to analyze soil water potentials in systems at equilibrium. If you'd like to learn more about soil physics, I invite you to check out our website, soilphysics.okstate.edu.